What's up, everyone? Today we're starting our deep dive into PLONK. This will be part one of a two-part series where we unpack both the arithmetization behind PLONK and the protocol itself. PLONK is a well-known PIOP, a polynomial interactive oracle proof. It describes how to prove that a set of polynomial constraints are satisfied. But before we can understand the PLONK protocol, we first need to learn how to translate our desired computation into a format that this proof system can work with. This process is called arithmetization. In this first part, we're focusing entirely on PLONK's arithmetization, how we take a computation and express it as a system of polynomial constraints that PLONK understands. Then in part two, we'll build on that foundation and walk through the actual proof system, how the prover and verifier interact, and how these polynomial constraints ultimately become a zkSNARK. Super exciting stuff. Now before we dive in, let's talk about prerequisites. Because this video ties together a lot of concepts from earlier discussions, ideally you've seen all the previous videos. But if not, at a minimum, you should have a basic understanding of fundamental definitions like constraints, and most importantly, a solid grasp of polynomials, why and how they're used, and how to interpolate a set of equations into one polynomial equation. With these concepts in hand, you'll be ready to follow along as we step into PLONK's arithmetization. Alright, let's jump in and get started. Let's start by zooming out and remembering the big goal of this whole series. We want to build a proof system that works for any arbitrary computation. To do that, we need a way for a prover to convince a verifier that a computation was done correctly, without the verifier having to redo all the work. That's exactly what PLONK helps us achieve. But PLONK doesn't work directly on code or computations. Instead, it works on algebra, specifically polynomial constraints. So before we can dive into the protocol itself, we first need to rewrite our computation into a form that PLONK can understand. In other words, we need to translate it into an algebraic structure that captures the computation's behavior. Once we've done that, PLONK can step in and handle the proof part. So here's the first key idea. Any computation over finite inputs that eventually halts can be broken down into a series of additions and multiplications in a finite field. Let's walk through a few examples to make this idea concrete. Alright, let's start with a simple example. Say our computation is w cubed minus 4w squared plus 9w minus 10. We can break it down into just additions and multiplications like this. W times w times w minus 4 times w plus 9 times w minus 10. Easy enough. Now, of course, real-world computations like a hash function are way more complicated. They might involve thousands of operations. But here's the thing. At the very core, the computation can still be broken down into a big sequence of additions and multiplications. Now let's look at something that looks more like a real computer program, which is, of course, also a computation. So how do we turn this into algebra? We can actually rewrite it using just additions and multiplications like this. b times x plus 3 plus 1 minus b times x minus 2. This only works if b is either 0 or 1. If b is 1, the first term survives and the second term disappears, leaving us with x plus 3. If b equals 0, the first term disappears and the second term survives, leaving us with x minus 2. Cool. We've taken a branching if-else computer program and turned it into pure arithmetic. This is a simple example, but the same idea scales up. Loops, conditionals, and even complex programs can all be reduced to a big sequence of additions and multiplications. Sure, it might take a lot of variables, but in principle, any finite computation that halts can be expressed this way. Now let's move into the proof setting. Let's call the output of this function y. Suppose a prover claims that for some values b and x, the output of our function is indeed y. But what does it actually mean to prove that? It means showing that b, x, and y satisfy the algebraic relationships that define the function. In other words, we're checking that these values fit together exactly the way the function says they should. To do that, we need to write constraints. Our first constraint comes straight from the arithmetic expression we saw earlier. Y equals b times x plus 3 plus 1 minus b times x minus 2. We also need to make sure that b is either 0 or 1, because that's what makes this arithmetic representation of the branching logic work. For that, we add a second constraint. B times b minus 1 equals 0. This works because the only numbers that satisfy this equation are 0 and 1. Together, these two constraints fully capture our function in algebraic form. And that's exactly the kind of thing a prover can prove in PLONK. So the idea is this. If a prover can provide values of b, x, and y that satisfy both of these constraints, then the verifier knows the computation is correct and doesn't have to run the program themselves. They just check the constraints. Great. Now let's revisit the previous example to help solidify this concept. Suppose we want a prover to prove that they know a value w, such that w cubed minus 4w squared plus 9w equals 10. We can rewrite this computation as a constraint. W times w times w minus 4 times w plus 9 times w minus 10 equals 0. So what does it mean to prove knowledge of such a w? It means the prover can actually provide a concrete value of w that satisfies this constraint. In other words, they're not just claiming a solution exists, they're exhibiting one. Notice the pattern? Both examples follow the same idea. We start with the computational statement and rewrite it as one or more algebraic constraints. Now that we got a feel for how to translate arbitrary computations into constraints, we're ready to explore the next step, structuring these constraints in a way that PLONK can work with. Hopefully by now, I've convinced you that any finite computation that eventually halts can be expressed using just additions and multiplications, and that we can capture correctness using constraints. Now let's take it one step further. PLONK is designed to handle all of these computations, but as we've seen, different constraints can look very different. Some involve a single multiplication, others multiple multiplications, and some are just additions. If we want a single proving system to handle all of these uniformly, we need every constraint to fit a standard template. In this template, there must be at most one multiplication between variables. Variables can be multiplied by constants, a certain number of these terms can be added or subtracted, and one constant term can be added or subtracted. Now you might be thinking, what if a constraint involves more than one multiplication? No problem. We just break it into smaller constraints and introduce intermediate variables to carry the results from one constraint to another. This way, no matter how complex the original constraint is, we can rewrite it entirely using the standard PLONK-friendly template. Let's revisit our example, w cubed minus 4w squared plus 9w equals 10. We rewrote this computation as the constraint w times w minus 4 times w plus 9 times w minus 10 equals 0. But notice something, this constraint contains multiple multiplications between variables. For example, w times w already involves two multiplications. That doesn't fit our template. So what do? We introduce intermediate variables. Let's call them t1, t2, and t3, and break this one large constraint into smaller ones that follow the template, like so. Now each constraint has at most one multiplication between variables, just like the template requires. And together, these four smaller constraints are equivalent to the original one. If all four are satisfied, then the original constraint is satisfied. Originally, with a single big constraint, the prover only had to provide a value for w to prove knowledge, since that was the only variable. Now, because we split it into smaller constraints, the prover needs to provide values for w, t1, t2, and t3. These values are called witnesses. Instead of proving one big constraint, the prover is now proving that all four smaller constraints are satisfied at the same time. But logically, nothing has changed. We've just reorganized the problem so it fits PLONK's template. Next, let's move everything to the left-hand side so that each constraint equals 0. One thing to notice here, by following the template, each constraint involves at most 3 variables. For example, in the first constraint, the variables are w, and t1. This isn't a coincidence. It's exactly what lets all of these constraints fit into the single unified template that PLONK can work with. And this brings us to that standard template, which is called the PLONK main gate. QL times A plus QR times B plus QM times A times B plus QO times C plus QC equals 0. This is really just a generalization of everything we've written so far. Every single one of our constraints can be expressed in this form. Let me show you how. Here's the idea. Each constraint is one instance of the PLONK main gate, which has exactly 3 variable slots, A, B, and C. These line up perfectly with the 3 variables in each of our constraints. The Q's, called selector coefficients, are fixed constants that define the specific constraint. Once we walk through an example, you'll see exactly how this works. For our first constraint, the variables are w, and t1. We can now map these to the 3 variable slots in the main gate, A, B, and C. Now what values do the Q's, the selector coefficients, need to take in order to encode this constraint? We see that if qm equals 1 and qo equals -1, and all the other q's are 0, then we end up with 0 times a plus 0 times b plus 1 times a times b plus negative 1 times c plus 0 equals 0, which is exactly our original constraint. We've just swapped the variable names from w and t1 to a, b, and c. So you can see how the PLONK main gate naturally captures this constraint. The template is general enough to represent it exactly. Let's move on to our second constraint. This time the variables are t1, w, and t2. Again, we map them into a, b, and c. Looking at the selector coefficients, if qm is 1, qo is negative 1, and the rest of the q's are 0, we get 0 times a plus 0 times b plus 1 times a times b plus negative 1 times c plus 0 equals 0. And just like before, the PLONK main gate captures this constraint perfectly. Now for the third constraint. This one has no multiplication between variables. It's purely linear. The variables are t2, t1, and t3, which we represent with a, b, and c. Here the selector coefficients are ql is 1, qr is negative 4, and qo is negative 1, with the other q's being 0. Notice that qm is 0 because there is no multiplication between variables. Plugging it in, we get 1 times a minus 4 times b plus 0 times a times b plus negative 1 times c plus 0 is 0, which matches our constraint. And there you go. Even purely additive constraints fit naturally into the PLONK main gate. Finally, our last constraint only has two variables, t3 and w. That's fine, we'll use a and b for these, and c can be anything since it won't affect the equation. The selector coefficients are ql equals 1, qr equals 9, and qc equals negative 10, with the rest of the q's equal to 0. Since qo is 0, and 0 times anything is 0, it doesn't matter what c is. Plugging it in, we get 1 times a plus 9 times b plus 0 times a times b plus 0 times c minus 10 equals 0. And that exactly reproduces our final constraint. And here's the key takeaway. One universal constraint, the PLONK main gate, can capture every constraint in our computation, no matter how many intermediate variables or steps we need to introduce. To keep everything organized, we'll add subscripts to the variables and selector coefficients. We'll be zero indexing, so we will use 0 for the first constraint, 1 for the second one, 2 for the third, and 3 for the fourth. Now, a natural question arises. Who sets the values of the q's, and who sets the values of the a, b, and c's? The selector coefficients, the q's, define the constraints. Once they're fixed, the form of each constraint is completely determined. In other words, the q's set the rules of the game. They determine exactly what is being proven. Because of this, the q's must be fixed ahead of time. The prover can't change them. If they could just redefine the constraints and prove anything. The prover's job then is the following. Given the fixed q's, they supply the witness values, the numbers that go into the a, b, and c slots, in a way that satisfies all the constraints defined by those selectors. From the verifier's perspective, they are only convinced if the prover can satisfy this specific set of constraints, as defined by the fixed q's. So how do we make sure that the q's are fixed? The answer is straightforward. Both the prover and verifier have access to the same set of q's ahead of time. Since both parties know the q's, the prover's job is simply to provide witness values that satisfy these selectors to generate a proof, and the verifier checks the proof against the same fixed q's. If the prover tried to generate witness values for a different set of q's, the verifier would detect it. The proof would fail because they would always check it against the beforehand agreed upon q's. Now that we understand the role of the q's and the witness values, let's go back to our example and talk about efficiency. I'm going to rewrite our 4 constraints now as they look in the PLONK main gate form. You might be wondering, how does PLONK check all these constraints efficiently? In our example, we only have 4 constraints, but what if there were 1,000 or even 1,000,000? The answer is that we can encode them into polynomials. This is where the foundation from the polynomials video really pays off. You'll remember that a single polynomial can encode information about multiple equations at once. If that idea isn't fresh, it's worth reviewing because it's the key to understanding this next step. Think of the PLONK main gate constraints as forming a matrix. Each constraint is a row, and each selector or variable, the q's and a, b, c, is a column. Now let's use the row number as the x value for interpolation. The first constraint corresponds to x equals 0, the second to x equals 1, and so on. By using these values as evaluation points, we can interpolate a polynomial for each column. QL of x, A of x, QR of x, B of x, QM of x, QO of x, C of x, and QC of x. Evaluating a polynomial at a row's x value gives exactly that value from that row. This should feel familiar if you watch the polynomials video. It's the same idea of encoding multiple points into a single polynomial. With this in place, we can now write a single polynomial constraint. QL of x times A of x plus QR of x times B of x plus QM of x times A of x times B of x plus QO of x times C of x plus QC of x equals 0. Instead of checking each row individually, we now only need to check that this polynomial equation equals 0 at the evaluation points x equals 0, 1, 2, and 3. And this is the key to efficiency. No matter whether we have 4 constraints, 1,000, or 1,000,000, we can reduce them all to a single polynomial constraint that must hold at the specific evaluation points. As we mentioned before, the q's are fixed and shared with the verifier before proving begins. That means the selector polynomials, QL of x, QR of x, QM of x, QO of x, and QC of x, are created and shared ahead of time. During proving, the prover fills in the witness values, a, b, and c, for each row, and then interpolates them to form the corresponding polynomials, a of x, b of x, and c of x. These polynomials are what the prover uses in their proof. One thing to note, in practice, instead of using x equals 0, 1, 2, 3 as our evaluation points, we use the roots of unity. This makes it possible to perform interpolation much faster using an inverse FFT instead of the slower Lagrange interpolation. It reduces the prover's runtime from O of n squared to O of n log n. But the key intuition stays the same. The rows of constraints are captured by interpolating them into polynomials, and instead of checking each constraint individually, we just check that a single polynomial constraint holds at all the evaluation points. That's how PLONK can handle thousands or even millions of constraints efficiently. By the way, what I've just described is known as vanilla PLONK arithmetization, the original construction from the PLONK paper. The key idea is to have one consistent template that every constraint can fit into. In this case, the PLONK main gate format we've been using. You can imagine variations of this approach though. For example, someone might design a template that allows 2 multiplications per row instead of 1. That could reduce the total number of constraints, which can be good for efficiency, but each constraint becomes more complex, which might hurt efficiency instead. The main point is that as long as the template can represent all possible constraints, it works. Different projects and teams have made their own modifications to suit their needs. This is why more generally, we call this PLONKish arithmetization. It's PLONK-like, but not necessarily the original vanilla version. For now, we'll stick with the vanilla PLONK arithmetization, since our goal is to build intuition. At this point, we fit all of our constraints into the PLONK main gate format, but that's not the full story yet. So, if the prover can provide witness values that satisfy each constraint individually, are we done? Not quite. Right now, each constraint is treated independently, but in our original computation, some variables are supposed to be shared, both within a single constraint and across multiple constraints. For example, our first constraint was w times w minus t1 equals 0, and the second was t1 times w minus t2 equals 0. That means the two w's in the first constraint need to be the same value, which also need to be the same as the w in the second constraint, and t1 from the first constraint must match the corresponding t1 in the second constraint. In PLONK notation, the first constraint has variables a0, b0, c0, and the second has a1, b1, c1. So what we need to do is force the prover to use the same value for a0, b0, and b1, the w's, and the same value for c0 and a1, the t1. If we don't enforce this, the prover could cheat by giving different values for the same variable, and each individual equation would still appear correct, but the overall computation wouldn't be valid. Here's a simplified example to show what could go wrong. Suppose we have the computation w cubed equals 27. So the prover wants to prove they know a value of w that satisfies this. Spoiler, the answer is w equals 3. Using what we've learned, we can break this into 2 constraints. W times w equals t1, and t1 times w equals 27. Moving everything to the left-hand side, we get the following. We can express these using the PLONK main gate. For the first constraint, we have qm equals 1, qo equals -1, and the rest, ql, qr, and qc, are 0. For the second constraint, we have qm equals 1, QC equals negative 27, and the rest of the Qs are 0. Now imagine a malicious prover tried to cheat and filled in A0 equals 5, B0 equals 5, C0 equals 25, and A1 equals 27, B1 equals 1, and C1 equals anything. Both constraints would still be satisfied individually, but that doesn't prove that the prover knows W equals 3, which is what we actually want. What we really need is to enforce that certain witness values are equal. In this example, A0 must equal B0 and also equal B1, since they all represent the variable W. And A1 must equal C0 since they represent the variable T1. If a prover violates these equalities, like in our malicious example, they should fail, even if each individual main gate constraint looks fine. So the question becomes, how do we create constraints that force the prover to provide witnesses where certain ones must be equal? This is exactly what the copy constraints handle. In this example, we have two copy constraints. A0 equals B0 equals B1, and A1 equals C0. These constraints ensure that whenever the same variable appears either multiple times within a single constraint or across different constraints, the prover assigns it the same value everywhere. In other words, it enforces full consistency of repeated variables. So how do we enforce this kind of consistency? To answer that, we need a small but important detour, because the tool PLONK uses to enforce these copy constraints is called the permutation argument. And at its core, the permutation argument boils down to a simpler question, which we'll look at first. How can we check that two multisets are permutations of each other? A multiset is just a collection of values where duplicates are allowed. For example, consider D equals 7355 and E equals 7535. Both D and E are multisets, and they're permutations of each other because they contain exactly the same values with the same multiplicities. For example, they both contain two 5s, just in a different order. For small examples like this, we can tell that they're permutations just by looking at them. But how could we check this mathematically? Here's a neat trick. Build a polynomial whose roots are exactly the elements of the multiset. So for multiset D, define d of x as x minus 7 times x minus 3 times x minus 5 times x minus 5. And for multiset E, define e of x as x minus 7 times x minus 5 times x minus 3 times x minus 5. Now here's the key idea. If two multisets are permutations of each other, then these polynomials, d of x and e of x, will be identical. Why? Because multiplication is commutative. The order of the factors doesn't matter. So rearranging the elements of the multiset just rearranges the factors of the polynomial, which doesn't change the final result. In our example, since D and E contain exactly the same elements with the same multiplicities, their corresponding polynomials are equal. That gives us a clean algebraic way to test multiset equality. But notice something important. This method does not check which permutation was used. It only checks that the two multisets contain the same elements with the same multiplicities. For example, another multiset F, which equals 7553, would also pass this test, because it contains exactly the same elements. In fact, any permutation of D would produce the same polynomial. So here's the real question. Can we extend this idea so that we don't just check that one multiset is some permutation of the original, but rather it is a specific, predefined permutation? For example, instead of merely checking multiset equality, suppose we want to check if a multiset is a permutation of the original, where the second and third elements are swapped. That is, 7355 is permuted to 7535. Now the requirement is stricter. We want E to pass because it reflects that exact positional swap. But F should fail, even though it contains the same values, because the elements are not in the positions dictated by that specific permutation. So the question becomes, how can we algebraically enforce a specific permutation of positions? Let's write the permutation we want in numbers, relative to the original multiset. Our original multiset is D, which equals 7355, and we label the positions in ascending order as 0, 1, 2, 3. This gives us a clear reference for defining the permutation. We want to check a permutation that swaps the second and third elements, so the desired permutation is 0, 2, 1, 3. Now we'll enhance each element by putting it into a tuple with its position. For the original multiset D, we create a new multiset D prime of these tuples, 0, 7, 1, 3, 2, 5, 3, 5. For the set we are testing, we apply the desired permutation to the positions. So for set E, this gives us a new multiset E prime of tuples 0, 7, 2, 5, 1, 3, 3, 5. Note that D prime and E prime are equal multisets of tuples. Well, what about F? F equals 7, 5, 5, 3. Pairing with the desired permutation positions gives us F prime equals 0, 7, 2, 5, 1, 5, 3, 3. Note that there is no 1, 5 tuple in D prime, so F prime fails this test. D prime and F prime are not equal. Here's the key idea. By pairing each element with its intended position, we've encoded the specific permutation into the multiset itself. Then by checking that the new multisets have the same tuples, we can enforce that the permutation was followed exactly. So again, it's great that we can tell this just by looking at the tuples, but we want a way to check it mathematically. How can we verify that two multisets have the same tuples? We can basically use the same trick as before. Build a polynomial whose roots are exactly the elements of the multiset. The difference now is that the elements are tuples, not just single values. But we can turn tuples into single values by combining their components in a linear way using a new variable. This lets us encode each tuple as a single field element. Once that's done, we can construct polynomials for each multiset and check equality of these polynomials, just like we did for the multisets before. Let me show you how to do this for a running example so you can see it in action. You can see that this is basically just an extension of what we did before. For each tuple, we're now taking a linear combination of its two components using the variable y to combine them. This turns each tuple into a single value that can serve as a root in the polynomial. Now, if d prime of xy and e prime of xy are equal, that means the multiset E matches the specific permutation we defined. Try applying the same trick to f yourself. You'll see that the corresponding polynomial f prime of xy won't equal d prime of xy, showing it doesn't satisfy that permutation. That's great, we found a way to use polynomials to algebraically check if one multiset is a specific permutation of another. But you might be wondering, how does this connect back to our original problem, ensuring consistency of witness values in PLONK? Let's go back to our super simple example with the computation w cubed equals 27. Recall our constraints. And after putting these into PLONK main gate form, we have this. Now we're going to assign each witness a unique index starting from 0. We'll go in order, all the A's first, then the B's, then the C's. So A0 is assigned index 0, A1 1, B0 2, B1 3, C0 4, and C1 5. The witness values are analogous to our original multiset D. Our positioning ordering is 0, 1, 2, 3, 4, 5. Thus, the corresponding multiset of tuples is D prime, which is the following. Now we look at our copy constraints. A0 equals B0 equals B1, and A1 equals C0. For each copy constraint, we assign each witness to the position of another witness in the same copy constraint. This reshuffling creates a prescribed permutation that enforces the equality we want. So for the first copy constraint, we have the witnesses A0, B0, and B1, which are originally at indices 0, 2, and 3. We rearrange them, so now A0 is index 3, B0 is index 0, and B1 is index 2. For A1 and C0, originally 1 and 4, we rearrange them to 4 and 1. The remaining witness C1 stays at its original index, 5. Our new ordering is therefore 3, 4, 0, 2, 1, 5, which is our desired permutation. Therefore, the multiset of tuples becomes the following. Pause and compare D prime and E prime side by side. You can see that these multisets will only match if A0 equals B0 equals B1, and A1 equals C0. In other words, the multisets will only match if the copy constraints hold. Just like before, we can then construct polynomials d prime of xy and e prime of xy and check their equality. If these two polynomials match, that tells us the specific permutation is satisfied, and therefore any witness values that were supposed to be equal really are equal. The exact protocol is slightly more involved, so we'll cover the exact details in the next video. But for now, here's the key takeaway. By fixing a specific permutation, we can turn the consistency requirement between witnesses into a polynomial identity check. This is how PLONK uses the permutation argument to enforce the copy constraints, ensuring that certain witnesses are equal across the table. Just like the selector coefficients, the Q's, the specific permutation must be fixed ahead of time. The prover can't be allowed to change it. So what do? We do the same thing as with the selector polynomials. We create fixed permutation polynomials well before any proving begins and share them with both the prover and the verifier. These permutation polynomials encode the specific permutation that must be enforced. The prover uses these polynomials when generating the proof, and the verifier uses the same ones when checking the proof. Because both parties rely on the same fixed polynomials, the permutation is locked in, ensuring the prover can't secretly alter the copy constraints. Let's see how to create the permutation polynomials for our example. Our prescribed permutation is 3, 4, 0, 2, 1, 5. We interpolate separate polynomials for the a's, the b's, and the c's. Since we have only 2 rows in this example, we use x equals 0 for the first row and x equals 1 for the second row as our evaluation points. Then we get SA of x, the polynomial which equals 3 at x equals 0 and 4 at x equals 1. SB of x, which equals 0 at x equals 0 and 2 at x equals 1. And SC of x, which equals 1 at x equals 0 and 5 at x equals 1. The polynomials SA of x, SB of x, and SC of x are our permutation polynomials, and these are what get shared with both the prover and verifier ahead of time. Note that in a real system, though, we would interpolate over the roots of unity. X equals omega to the 0, omega to the 1, and so on, instead of x equals 0, 1, and so on. But the idea is exactly the same. And that's it. We've covered a lot today, so let's recap. Today we talked all about PLONKish arithmetization, which turns arbitrary computation into a format that PLONK can understand. We can take something like proving you know a preimage to a hash, or proving that certain inputs and outputs are valid for a computer program, and rewrite it as a set of algebraic constraints. In vanilla PLONK arithmetization, these constraints all fit into a single template called the PLONK main gate. Using polynomials, we can turn many of these constraints into one polynomial constraint. The Q's are called selector polynomials and define the constraints. These are fixed ahead of time and shared between the prover and verifier. The A, B, and C values are witnesses and are only filled in during proving. We also learned that we need to define copy constraints, which specify that certain witnesses must have the same value. We learned about the permutation argument, which is used to enforce these copy constraints. The predefined permutation is encoded into SA of x, SB of x, and SC of x, and like the selector polynomials, these are fixed and shared ahead of time. From the verifier's perspective, we are essentially saying, if the prover can supply values for A, B, and C that satisfy all the main gate constraints, and use the permutation argument to satisfy the copy constraints, then the computation is valid. Great, we came a long way today, so take a moment to review everything carefully. Getting these foundations solid will make the next video, where we dive into the PLONK protocol itself, much easier to follow. Thanks for watching, and see you next time.